All right, today we're going to learn about forces. In middle school, you probably heard that a force is a push or a pull, and you probably were given examples of somebody pushing on a box and making it move, or pulling on a box and making it move, and that is a great introductory example. But if you look at our definition here, it says that we have a force that is a push or a pull that has the ability to change the motion of an object. So we're going to talk a little bit about the ability to change the motion of the object. When we say that it has the ability, this means that a force could change the motion of an object, which is probably what you see most often in previous examples. But we could also have a force that is present and not accomplish any kind of change or have any overall effect on our object. And so that's where oftentimes students struggle a little bit with understanding that we have forces present when there is no change to our object's motion. So that's what we are going to be focusing on as we go through our examples, having forces present, and we may or may not see an effect from that force. So it says here that it has the ability to change motion. So we're going to talk about that real quick. If we were to be using our vocabulary, we would replace the phrase change motion and we would just call that our acceleration. A force has the ability to cause objects to accelerate. Now, how can objects accelerate? They can speed up, slow down, or they can change direction. So we can have a force present, and that force may cause the object to speed up, slow down, or change direction, or that force may have no overall effect on our object. Forces are going to be measured in newtons, and so we're going to use a capital N for the unit newtons, and we will use a capital F for the variable force. Now, there are a few different types of forces that you will need to become familiar with. Applied forces are probably the most common examples. So this would be, I come up and I push the box. I'm holding my ID and I pull on the lanyard. I kick a soccer ball. Those are all going to be applied forces. So we're going to have a capital F for force, and we are going to use subscripts to help us understand what kind of force we are dealing with. So if we have a force that is an applied force, we're going to put a capital F for force, and we're going to put a subscript of a capital A. Now, please be careful here. I would not recommend that you choose to use a lowercase a, because in this chapter and in previous chapters, lowercase a means acceleration. And again, we could have a force present with no acceleration, right? It has the ability to accelerate, but it doesn't guarantee. So capital F, capital A for applied force. Our frictional force is going to be noted with a capital F for force, lowercase f for friction. And this is a force that's going to oppose the motion or going to oppose the intended motion. And I'll come back on that second explanation later. The force due to gravity is going to be a capital F for force and then a subscript of a lowercase g. Now, we've already talked about the acceleration due to gravity, which we saw as an AG, and we used a value of negative 9.8 for that. We'll come back to that and we'll use that value again later in our discussion, but for right now, this is not the same thing as the negative 9.8 meters per second squared. Remember, meters per second squared made it an acceleration. Now we are talking about forces. Forces are measured in newtons. So when we talk about the force due to gravity, make sure that you are not telling me that it's negative 9.8, because that value is the acceleration rate and it's measured in meters per second squared. Our normal force is going to be a capital F for force and then a capital N for normal. So here it says the normal force opposes gravity. In our class, we are going to have our normal force opposing gravity. And it says that it is due to contact with a surface. So we are going to have objects that are on the floor. Maybe it's a box that gets pushed across the floor. Well, the floor is going to apply a force upward onto the box, causing that box to become balanced, and I'll talk about what that means in a minute. But we know that gravity is pulling down on the box, so if we remove the floor, we would expect that box to fall, right? We would expect gravity to pull that box downward. But because the box is on the table, on the floor, if it's a car on a road, then that surface is pushing back up onto our box. So when we talk about the normal force, we are talking about that upward force because of the contact with that surface. We're going to keep our examples pretty simple in here. So our surface is going to be a flat horizontal surface, so that normal force is going to be pointed up for us most of the time. Okay, here it says this is vocabulary for future discussions. Okay, in the future, we'll come back to this for a later lesson. The word inertia is an object's resistance to change, and it's dependent upon the object's mass. Mass is a vocabulary word that you should have learned in chemistry class, and it's a way of quantifying how much matter it takes to create an object, and that is going to be measured in kilograms. Weight is a force. So this is something that we're going to need time for our brains to process. Weight is a force, and therefore it's going to be measured in newtons. This is the force specifically caused by gravity pulling down on our objects. And you can see over here, we're going to notate mass with a lowercase m, and weight is going to be an FG. Okay, we'll come back to that at a later conversation. So here is a list of the types of forces that you will be expected to recognize. We are going to create diagrams, and we're going to show all of the forces acting on our object. When we do this, we're going to need to label each of those forces. So FA we have already given to you. This is your applied force. And so this is that push or that pull or that kick. Our frictional force, FF, is going to oppose motion. So if I have a table and I have a book on top of the table and I want to slide the book across the table, well, there is friction between the table and the book. And so that friction is going to point in the opposite direction from whatever direction I am sliding that book, okay? So my frictional force, FF. Fg is the force due to gravity, and this will always point downward. We will never have it point any other direction for gravity. Fn is the normal force, and so remember this is often due to contact with a surface like a table or a road or something like that. So for us, this will typically be pointing upward. Then we have Fb, which is buoyancy, and so this would be a situation where the water is pushing up on an object. So if you think about a sponge floating in the water or a boat sitting on the water is pushing up on that object. So the normal force in this case is not coming from a flat surface or a road. It is coming from the surface of the water. So we're going to call that F buoyancy, and that'll point upward. Ft stands for tension, and so this is any time we have a string or a rope or some sort of handle or thing like that. So here we could call our tension force our applied force, but if we understand that the question says I am pulling on a string, I am pulling on a rope, I would prefer you call it F tension. And then FL stands for lift. This is a form of air resistance where the air is pushing upward on the object. So if we have something like our airplanes where the air is pushing up on the wings, that specifically would be lift. Now, air resistance is a type of frictional force. So when we talk about F friction, this is opposing the direction of the intended motion. If it's something like I said before of a table and we've got a box, if the box is moving to the right, then frictional force will be to the left, and this would be rubbing friction between those two surfaces. But if we have something like an object that is falling or a bird that is flying, if that object is experiencing motion downward, then our frictional force, aka air resistance, would be upward. If we have an object that is moving through the air and that object is moving horizontally forward, then we would have our frictional force moving in the opposite direction. And so air resistance could be identified as a frictional force. It just depends on what situation we are given in the story. So these are the different types of forces, and I would like for you to label your force vectors with the appropriate name. Now we're going to learn how to draw free body diagrams. So free body diagrams are specific illustrations of all of the forces that are acting on an object. We are going to illustrate our forces with vectors. So just to review, a vector has magnitude and it has direction. Sorry about that. Let me switch this over. A vector in general has magnitude and direction. So we are going to use arrows in order to illustrate our forces. The length of the arrow is going to give us the magnitude. Obviously, the pointy end of the arrow is going to give us the direction. Okay, we're going to show all of the forces that are acting on our object. So what forces are present? The forces that are acting on the object may or may not cause an acceleration. So we have to understand the situation and think about, is there a force acting? Where is that force coming from? And we're going to label that, okay? All of our objects are going to be illustrated as boxes. So my airplane is a box. The egg falling is a box. The bird is a box. The box is a box, okay? Our object is always a box. And we need to draw our force vectors so that all of our vectors are pointing outward. So we are going to create free body diagrams where all of the forces are pointing outward from the box, okay? All right. After we create our drawings, we are going to evaluate our picture. That picture is going to help us determine whether or not the object experiences a change in its motion. We're going to evaluate vertical arrows. So if we have a picture that looks like this, our vertical arrows are going to be analyzed to determine whether the object experiences an acceleration vertically. If we have an object with horizontal arrows, then those horizontal vectors are going to be analyzed to determine if there is a horizontal acceleration. And so that's how we're going to evaluate our picture. If we have balanced forces, then we are going to say that the object experiences no change in its motion, or we could say balanced forces mean no change, or we could say no acceleration. If we have unbalanced forces, this is a situation where my force vectors are not the same size. They're pointing in opposite directions, but one is longer than the other. You could perhaps have a situation where there's only one force, and so horizontally or vertically speaking, it would be unbalanced, okay? So if we experience unbalanced forces, then the object will have a change in its motion. And as you can see here, I've said or, we can say the object experiences an acceleration. So this is where we have to be able to draw those free body diagrams, and we need to draw them accurately so that they can help us evaluate whether or not the object accelerates.